Hey guys, Lainey here, and today I'm going to compare 5 LRFD drilled shaft examples from NCHRP 24-17 Appendix D. Each example represents a different subsurface condition, including clay, sand, layered sand and clay, and 2 cases involving intermediated geomaterials. The purpose of this comparison is to demonstrate how drilled shaft design changes depending on soil type and construction conditions, and how LRFD captures uncertainty through resistance factors. Rather than working through every equation, I will focus on how and why the design methods differ across these examples. At a high level, all drilled shafts resist load through the same 2 mechanisms: side resistance along the shaft and base resistance at the tip. That does not change. What does change is how those resistances are calculated and how confidently we can predict them. Drilled shafts are cast in place, which means we do not get installation feedback like blow counts. We excavate soil, place concrete, and the shaft cures underground. The construction process introduces uncertainty through disturbance, base cleanliness, and concrete to soil contact. LRFD accounts for that uncertainty using resistance factors, and those resistance factors vary depending on soil type, design method, and construction reliability. The first example is a drilled shaft in clay. Because the soil is cohesive and behaves in undrained conditions, the design uses the alpha method for side resistance. In this method, side resistance is calculated as alpha times the undrained shear strength. This reflects the adhesive bond between the concrete and the clay. Base resistance is calculated using traditional bearing capacity theory, but for large diameter shafts, that base resistance is often reduced. In this example, capacity is largely controlled by shaft resistance rather than end bearing. The resistance factor is relatively low, around 0.30, which reflects uncertainty in undrained strength variability, construction disturbance, and the sensitivity of clay to remolding. The second example is a drilled shaft in sand. Here, the behavior is completely different. Sand does not have undrained shear strength, so the alpha method is not appropriate. Instead, the design uses the beta method, where unit side resistance is proportional to effective vertical stress. Beta decreases with depth to account for stress relief and interface limitations. Side resistance increases with depth, but only up to a limit. Base resistance is calculated using SPT in values, but it requires larger settlement to fully mobilize compared to side resistance. Because sand behavior is more predictable when density is well characterized, the resistance factor is higher than clay, typically around 0.40, but still relatively conservative due to settlement sensitivity and construction effects. The third example involves a layered soil profile with sand over clay over sand. This example clearly shows how LRFD design adapts to varying subsurface conditions. Each layer is treated according to its governing behavior. The sand layers use the beta method, while the clay layer uses the alpha method. Shaft resistance is calculated separately for each layer and then summed. A key design point here is that base resistance must be checked against all layers influencing the tip, not just the material directly below it. The weakest controlling layer can govern performance. Because multiple mechanisms contribute to resistance and the profile is well defined, the resistance factor increases to around 0.50. At this point, it helps to compare what actually controls capacity in clay versus sand. In clay, capacity is controlled by undrained shear strength. Side resistance mobilizes very quickly with small displacement, and base resistance is often limited to control settlement. In sand, capacity is controlled by effective stress and density. Sand is strong, but it requires more movement to mobilize resistance, especially at the base. These fundamental behavioral differences explain why the alpha method is appropriate for clay while the beta method is used for sand. The fourth example introduces intermediate geomaterials, which behave somewhere between soil and rock. In these materials, strength-based methods alone are no longer sufficient. Instead, the FHWA O'Neill IGM method is used. This is a deformation-based approach that explicitly considers how load is transferred as the shaft displaces. Capacity is calculated at specific displacement levels, such as 2 mm and 5 mm. This method accounts for shaft stiffness, rock mass stiffness, and socket roughness. Rather than asking what the ultimate strength is, the method asks how much load can be carried at an acceptable displacement. The fifth example builds on the IGM approach but includes additional layering, with sand and clay above a limestone or weak rock. In this case, the clay is still treated with the alpha method, while the socketed portion in the IGM is analyzed using the deformation-based approach. Total capacity becomes displacement dependent, and different assumed settlements produce different capacities. Because rock-like materials offer more reliable load transfer when properly constructed, the resistance factor is the highest of all of the examples, typically around 0.75. When we step back and compare the resistance factors used across all 5 examples, a clear pattern starts to emerge. The resistance factors are not random, and they are not simply tied to how strong the soil or rock is. In the clay example, the resistance factor is the lowest. Clay behavior is highly sensitive to construction disturbance, variations in undrained shear strength, and assumptions about adhesion at the concrete-to-soil interface. Because small changes in construction quality can significantly affect capacity, LRFD reflects that uncertainty with the lower resistance factor. For sand, the resistance factor increases. Sand's strength is governed by effective stress and density, which are generally more predictable than undrained clay strength. However, sand capacity is still sensitive to settlement and base mobilization, so uncertainty remains and the resistance factor stays moderate. In the layered soil examples, resistance factors increase again. Multiple soil layers create redundant load transfer mechanisms, and capacity is shared across different materials. That redundancy improves reliability and reduces uncertainty in the overall system. The highest resistance factors appear in the IGM examples. This is because IGM design is explicitly tied to measured deformation. Instead of assuming full mobilization, capacity is evaluated at the specific settlements, which makes the prediction more reliable. This highlights an important LRFD concept that resistance factors reflect uncertainty in how well we can predict behavior, not simply how strong the ground is. To summarize, LRFD drilled shaft design is not just an exercise in plugging numbers into equations. The soil type fundamentally controls the design method, how resistance is mobilized, and which assumptions are appropriate. In clay and sand, design is largely strength-based and relies on empirical correlations such as alpha factors, beta factors, and SPT values. These approaches work well, but they can carry uncertainty because they depend on simplified representations of complex soil behavior and construction effects. In contrast, intermediate geomaterials require a deformation-based approach because displacement governs performance rather than ultimate strength alone. By explicitly evaluating load transfer with movement, the IGM method provides greater confidence in predicted capacity. As uncertainty and behavior decreases, resistance factors increase. Across these 5 examples, LRFD consistently ties reliability to our confidence in the prediction method. Together, these case studies show how LRFD integrates soil behavior, construction effects, and engineering judgment to produce safe and rational drilled shaft designs. These 5 examples show that LRFD drilled shaft design is not a one-size-fits-all, and that soil type, load transfer, and uncertainty drive both the design method and resistance factors. Thank you for watching.